All right, so we're going to finish up section 6.1, which is on angles and their measures. We're going to look at what's called arc length. I think we're going to look at angular velocity, and that's it. Those are the only two things we're going to look at. All right, so arc length is basically, we're going to come up with a formula that gives us a way to find out on a circle how big of an arc you traced out given an angle. They'll tell you how big of an angle to draw, and you're going to find the length of an arc like that. Okay, but one thing we have to know going into it is that arc size and angle size are directly proportional. All that means is if you, let's say you had a circle, and in that circle I sketch a 90-degree angle, right there, hits the edge of the circle, and it makes an arc in blue right there. So how big is that angle in black?
90.
Yeah, that's a 90. All right. So now, if I take, and instead of sketching a 90-degree angle, I'm going to double the size of the angle. Initial side, terminal side. Here's my arc. I doubled the size of the angle from 90 to 180. What happened to the size of the arc? Yep. It also doubled. That's because they're directly proportional. So you double the size of the angle, double the size of the arc. If you have the angle, you have the arc. So what that means is when we set up a formula, we're going to be able to set up a proportion because the two things are directly proportional. All right, so we're going to start by looking at this diagram. Okay, what I've drawn here is a circle with two angles inside it. I've labeled the two angles theta and theta 1. And I've labeled the arcs that correspond to those angles. I drew them in red. Arc S corresponds to angle theta. Arc S1 corresponds to theta 1. The reason I've got four things here is because I'm trying to set up a proportion. And the proportion is going to give me my formula. Now, the only problem with a proportion is you need something to start with. Right? A proportion has four blanks in it. Two numerators, two denominators. Like if we, and I'm going to go back to the example we did yesterday to convert between feet and inches. 12 inches in 1 foot. Now, I could have done 24 inches in 2 feet or 36 inches in 3 feet. There's lots of different things I could use here. I chose a 12 and a 1. Because I chose a 12 and a 1, does that limit what number I can put here or what number I can put there? Chris?
No.
No. If you want me to convert 73.4 inches, I can put 73.4 inches, cross multiply, and solve for x. Right? I just had to have something to start with, a fact that was true. Okay? So even though this is a very specific fact on the left, it doesn't limit what numbers you can use on the right. You can fill in any number you want for inches or for feet, one or the other. Okay? And then solve for the other one you're missing. So this is what we need to figure out. What can we start out with? And to figure that out, we're going to suppose that theta 1 is 1 radian. Because if we do that, something special happens in the circle. If theta 1 is 1 radian, then this arc is automatically the same as something else in the circle. Does anyone remember from yesterday? If this angle is 1 radian from here to here, then that arc in red is equal to the length of something else. That was the very first thing we said about radians. Before I even gave you formulas, I gave you a visual, and I said this is what a radian would look like. Yep?
The arc, or no, never mind.
Yeah,
Radius.
the radius. All right, so this is something very special. If you let theta 1 be 1 radian, then your arc is automatically the same size as your radius. That's going to be our starting fact. That's like our 1 foot, 12 inches. So if you say to me, well, what if theta 1 isn't 1 radian? Well, what if you decide not to put a 12 here? You could put a 24. You could put a 36. You just have to know the facts that goes with it. I chose a 1 because 1 is an easy number to work with, and this is the fact that goes with it. If theta 1 is 1 radian, then the arc equals the radius. That's just a definition. Okay, so now let's set up a proportion. There's lots of ways you can set it up as long as you're consistent on each side. So I'm going to do angle over arc equals angle over arc. So my first angle, theta 1, over my first arc, S1. And I know I'm going to plug some things in a second that we just said. But angle over arc. Does anyone have a guess what would be in the top of the other side? Yeah?
1 radian.
So we've used this, and we've used this, but we still have 2 more things we got to use in that diagram. Yeah. The theta. So, yep, and then the denominator on that fraction? S. So we compared, if you wanted to look at it, it's not necessarily to scale, but if you assume I drew things to scale, it's small angle compared to small arc equals big angle compared to big arc. That's our proportion. Now we're going to fill in. What we just said. If theta 1 is 1, then that automatically makes the arc R. Just like if you say 12 inches on the top, automatically makes the bottom 1 foot. Why? That's just a definition. That's the way it works. And on the other side, that's where your variables would be. Like over here. That's where you would plug in some other stuff they would give you in the problem. But for now, we don't have anything else, so we just leave it. Now, how do you solve a proportion? What do you do?
Cross multiply.
You cross multiply. So we get S times 1, which is just S, equals R times theta. And that is the arc length formula. S equals R theta. Okay, so there's 3 variables in that formula. The first variable is the arc. That's S. The second variable is the radius. That's R. And the last variable is the angle. And that's theta. But notice what I put in parentheses next to the angle. In radians. Because way back when we started this problem, we supposed that we were working with 1 radian. That's what we used as our starting fact. Okay. Just like if you use the formula 1 foot equals 12 inches, you're assuming the person is working in feet and inches. So whatever they put on the other side of that proportion, it's got to be feet and it's got to be inches. They can't put centimeters. That's not the unit that you started with. So the way the formula works is there's 3 things. They'll always give you 2 out of 3, and you solve for the third one. So let's look at an example. So this one, they drew a picture out. Really, you don't really need a picture. But it says find the length of the arc of a circle. Your circle has a radius of 2. And the arc is created by an angle of pi over 4 radians. So find the length of the arc. Okay, before I do that, can somebody just remind me what's the formula again for arc length? Yeah.
S equals R theta.
Yeah. S equals R theta. So now the question is to find the length of the arc. So what letter in that formula are they asking me to find? Yeah.
S.
S. I don't know S. I'm going to fill in everything else. What's R in this problem? Yep. 2. Okay, I'm not going to worry about the unit right now. I am going to at the very end. But when you're doing the arithmetic, you can leave it just as 2. And then the angle in this case is how much? Yeah. Pi over 4. The angle is supposed to be in radians. That's what the formula said. Is pi over 4 in radians? Yes, there's no little circle for degrees. Okay. So we multiply, and we get S equals 2 pi over 4, or if you reduce it, pi over 2. And we just found S. What is S again? It's the length of the arc. So when we put a label on that, the label should represent length. How do you know what length unit to use? Use the same unit they used in the problem. So what should I put for a label on pi over 2? Inches. So if you wanted to know like how long is that, roughly as a decimal, it's about 1.57 inches in the circle with that angle. Most of the time, they're not going to ask you to change that to a decimal. But if they did, that's how you do it. Any questions on that one? All right. Let's try this one. They're asking for something different. Okay, this time they're asking you to find the radius. And they're telling you the arc length is 3 pi. And the angle is 60 degrees. Well, let's write down our formula. Can I fill in for S? Do I know what S is? Okay.
It's 3 pi.
Yep. It's the arc length, and they tell me the arc length is 3 pi. So I've got that. We'll just go right through all the letters. Can I fill in for R?
No.
No, the directions say find R, so we don't know R. Can I fill in for the angle?
Yes.
Yeah. What should I put in?
60 degrees. Pi over 3.
Pi over 3. So remember, that if we go back to the formula, the angle has to be in radians. Okay. If you put 60, it won't work. So the first step would be doing what we learned yesterday, convert 60 degrees to radians. Okay, so now I want to get R by itself. Well, I'm multiplying by a fraction. So there is a way to get the pi and the 3 on the other side at the same time. Does anyone know what I would do on both sides? It's kind of like if you had something like this. And you wanted to move the 3 and the 4 at the same time. Yep. Yep, multiply by the reciprocal. So times 3 over pi, times 3 over pi. Pi's are gone, 3's are gone, and you get R equals, pi's are gone. 3 times 3 gives me 9. Now that's R. R is what kind of unit should we put on R? Feet. R is a length. So I go back in my problem, I look at their length units, they used feet, I'm going to use feet. Okay, and the third type, which I didn't do an example of, is where they would give you the arc length and the radius, and you would solve for the angle. So we solved for R, and we solved for S. Any question on how you would solve for theta? It would just be S divided by R, and that's it. Be careful when you solve for theta, because if the directions say leave the answer in radians, you're done. If the problem said convert your answer to degrees, then you would have to change what the formula gives you to degrees after. Okay, so angular velocity. So there's a way you can measure velocity, or the speed of something, if it's moving in a straight line. Like a car or something like that. So on your dashboard, there's usually something there that measures the speed. A lot of times it's miles per hour. In the US, might also have kilometers per hour if it's if it's a car that's used in other countries, things like that. But we usually use miles per hour. Well, that kind of unit is good for measuring the speed of something going straight. If you measure something spinning in a circle, the type of speed unit you're used to, like miles per hour or feet per second, it doesn't work very well. So I'm going to look at this diagram and we're going to see why we need angular speed. All right, so let's take a look at it. I've got 3 dots. Okay, I've got one in the center, the red dot in the middle, and the black dot on the outermost part of the disk. Okay, I'm going to make one revolution and bring that green handle back up to where I started. Right there. So all the dots just made one revolution. Which dot traveled the farthest? Yep.
The one closest to the outside.
Yeah, this one traveled the farthest. The one here looked like it didn't even move at all. So let's think about the distance formula. Distance equals rate times time, or distance divided by time equals the rate. Now, if you compare the speed it took for the middle one, the red one, and the outer one to do one revolution, how do those times compare for them to make that one revolution that I just did? Yeah. The times were all the same, right? So maybe it took 2 seconds for them to all make one revolution. So they all did something in the same amount of time, but one of them went further than the other. So what does that mean? If something goes further in the same amount of time as something else, what would that mean? Yeah.
It's going faster.
It's going faster. So if you think about speed the way we're used to thinking about it, the dot on the outside is traveling the biggest distance in the same amount of time as everything else. So if it's traveling further, it must be going faster. So that means every single point on this disk is traveling at a different speed, which is kind of confusing. So instead of describing the speed linearly, okay, like you would with miles per hour, we describe it angularly, right? Describing it in terms of like how many revolutions per minute the dots make. That way we can say the dots are all making, say, 1 revolution per minute or 10 revolutions per minute. They're all the same RPMs. And it makes it easier to think about. That's why we use angular speed. So angular speed, if they do not specify in the problem, is always measured in radians per whatever time unit. There's no set time unit. Radians per second, radians per minute, radians per hour. Doesn't matter. But it's always radians per something. Right? So there'll be some problems in the homework that say find the angular speed, and people are usually like, I didn't know what unit to use. Well, this is the default unit. You always use radians per whatever the time is. So comparing that to linear speed, that's measuring the speed of an object moving in a straight line, not spinning in a circle. That's why a lot of cars have 2 different gauges on them. They usually have one for your linear speed, right? Like, driving, and then the speed of the engine. It's measured in RPMs, the tachometer. So they don't measure like how many revolutions per minute the engine is making using linear speed. They use RPMs. Most cars, they don't use radians, they use revolutions. But it's the same idea. A revolution is just something spinning in a circle. Just like radians can measure something spinning in a circle. You could also use degrees. That measures something spinning in a circle. But most people are pretty familiar with RPMs. Like power tools, you might have like a drill, and it may spin at a certain speed. and it's usually measured in RPMs. Okay, so RPM's a little different than linear speed. Feet per second, miles per hour, kilometers per hour. Those are all examples of linear units because feet would measure something straight. Think of like a ruler, straight. Like miles measures something traveling straight. Same thing with kilometers. So the way we're going to convert between units is we'll use dimensional analysis. And we'll just think, okay, if we want to cancel out a unit, we'll make sure it's in the opposite spot on the fraction. So, for example, if you had feet in the top of a fraction and you wanted to cancel, you just make sure you put it in the bottom. So there are basic conversions you need to know. Anything with like basic units with time. How many seconds in a minute, minutes in an hour, hours in a day, days in a year. Okay, those conversions you need to know. How many inches in a foot, how many feet in a yard, how many feet in a mile. Those would be common ones. If something came up where you had to convert inches to centimeters, that's kind of a weird conversion. I would tell you that one. Okay, but yeah, it's 2.54 roughly. All right, so let's just practice converting 3 days to minutes. Okay. This is just a basic conversion. It doesn't have a rate. It's not like I'm saying you travel 3 days or, it takes you 20 minutes for an ant to travel 3 days or something. I don't know. I'm not saying it's a rate. It's just 3 days. And I want to convert to minutes. So what I do is multiply by conversion factors, one step at a time. So we're trying to get from days to minutes. What's the next smallest unit down from a day? Yep. An hour. Right? So I need a conversion between days and hours. What's the conversion between days and hours?
You would put 1 day on the bottom and you would put 24 hours on the top.
Yeah. So if you think of it, there's an invisible 1 there. I want days to cancel. So I'm going to put days in the bottom. And the conversion was just said. 1 day is 24 hours. Days in the top, days in the bottom. If you multiplied straight across, you would now have hours. Now we're going to go down to minutes. What's the conversion between hours and minutes? Okay. 60
minutes per hour.
60 minutes to 1 hour. Where do I want hours? Top or bottom? Bottom, because we want it to cancel. So, actually, I guess it's just hour, but that's fine. So in 1 hour, 60 minutes, hours, and hours cancel. And now you multiply straight across, and you get your answer. So 3 times 24 times 60. So 4,320. Any questions on that? Okay, let's look at this one. This one's a little different. This is a rate. So it's not just like 50 feet, and I'm saying convert feet to miles. I'm saying to convert 50 feet per second to miles per hour. So what does that mean? 50 feet per second. It means you travel how far in how much time? 50 feet in 1 second. 50 feet in 1 second. So it's kind of like you're doing 2 problems at the same time. So you've got to convert seconds to hours, and you've got to convert feet to miles. Start with converting seconds to hours. Next unit up from a second is getting bigger, is what? A minute. What's the conversion between minutes and seconds?
60 seconds equals 1 minute.
60 seconds is 1 minute. I put seconds in the top, so it would cancel over here in the bottom. Now if we start, we would have feet per minute. So we got to keep going. Next step up from a minute is an hour. So there's 60 minutes in an hour. where would minutes go here? Top
Top.
or bottom?
Top.
Top. 60 minutes in 1 hour. If we stop now, we'd have a speed in feet per hour. So my time unit is good. I got the time where I need it. Now I need to get feet to miles. So what's the convert? Well, even if we don't know the conversion, where does feet have to go? Top or bottom? Yeah, it goes in the bottom. And in 1 mile, there's a certain amount of feet. Does anyone know what the conversion is? That's why the metric system's a lot easier. Everything is based on 10, 100,000. We have all kinds of weird numbers like 12 and 1, feet to inches. But this is a pretty big number.
Oh, it's a big number?
Oh yeah. Well, it's in the thousands.
Oh, never mind then.
How many feet in a mile? Yep.
5,076.3.
There's no decimal. It is an exact number.
Oh, okay.
It is 5,000. Everybody knows how many feet in a mile. 5,280.
Did you just have that memorized?
Yeah. I think at one point, yeah, I must have learned it. 5,280. And now feet cancels. And that's it. So now if we multiply across the top, multiply out what's in the bottom, let's see what we get. So 50 times 60 times 60 times 1 divided by 1 times 1 times 1 times 5,280. I think I did that wrong. 50 times 60 times 60. 50, 60. Yeah, I went too fast. Divided by 5,280. 34.09 miles per hour. So you can put MI/HR, or a lot of people abbreviate miles per hour as MPH. It's the same thing. Or that. Any questions on that one? All right, so this, I think this is, yeah. So we'll do these two. We might start 6.2 part 1, but we're not, we won't finish it today because I don't want to rush through it. So we'll do a little bit of it, and then that'll give us some probably extra time on Thursday, so maybe we'll have like 40 minutes to review on Thursday. Probably won't have 80 minutes, but we'll still have half the class to review. All right, so 200 radians per second, and we're going to convert it to revolutions per minute. So 200 radians in 1 second. Let's deal with the time first. What could I multiply by to get seconds to minutes? Oh, Joe? To get seconds to minutes.
I have no clue.
Well, where would seconds have to go in that fraction? In the where? In the top. And what's the conversion between those two units?
60 seconds in a minute.
60 seconds in 1 minute. Okay, so we got radians per minute. Now we want to change radians to revolutions. All right. Even if we're not sure what the numbers are, we should be able to figure out where radians goes. Okay?
On the bottom.
Goes on the bottom. And this is something we did yesterday. I know there's 360 degrees in a revolution, but that doesn't help. I need how many radians in a revolution? 2 pi. Yep. So there's 2 pi radians in 1 revolution. And there you go. So let's multiply it out and see what we get. 200 times 60 divided by 2 divided by pi. So it's 1,909.9. 909.9 revolutions per minute. Which again you could write as RPMs. Or you could put revolutions per minute. Any questions on that? All right, the last one we'll do is this one. It says a wheel with a radius of 18 inches is rotating at 1,850 revolutions per minute. Find the angular speed in radians per second. I'm going to skip that because we just kind of did that. Right? I'm going to do part B. Part A is converting RPMs to radians per second. We just converted radians per second to RPM. So we just did it. It's just, it would be the reverse. But part B is a little different. Find the linear speed of a point on the circumference. So this is where you're thinking about that disk and you're imagining a point on the very edge of the circle. How fast is that point traveling if all of a sudden that point became unglued and it just flew off the disk straight? Okay. You could also think about it as you have a rope 18 inches long and you have a weight tied on the end of it and you're swinging the rope, or a machine is swinging it at 1,850 RPMs. If you let that rope go, it's going to take off straight in a direction. I want to know how fast it would be going. That's basically what part B is. Okay, so let's just start with what we're given. 1,850 RPMs. All right. Well, they want me to get seconds, so let's just get that out of the way. In 1 minute, there's 60 seconds. So now I've got revolutions per second. I have to change revolutions to feet. Where would revolutions go? Go in the bottom. Now this is a little tricky. How many revolutions or how many feet there are in a revolution depends on how big of a thing is revolving. Okay? So this is not a standard conversion. Like there's always 60 seconds in a minute. That never changes. But this conversion changes in every problem. Depends, again, how big of an object we have. What haven't we used yet in the problem that they told us? And this is going to tell us how big of an object we have. Yeah, Ron?
You would have to use the radius to find the circumference, right?
Yeah, we have to find the circumference. All right, so let's find the circumference. And remember, the circumference is a revolution. So if you know the length of the circumference in feet, that will tell me how, like if I were to pretend like that was a piece of wire and I cut it, and then I laid it out straight, I would know, I could measure how long it is, and I would know how many feet in one revolution of this tire. All right.
So it would be 2 pi times 18, right? That's the circumference.
So the circumference is 2 pi r, and it would be 2 pi times, now I'm going to kind of do something at the same time. They want it in feet. They gave me the radius as 18 inches. How many feet is 18 inches?
1.5.
It's 1.5. So instead of doing 2 pi times 18, I'm going to do 2 pi times 1.5 and jump to feet right away. Any question on that? Okay. So that's going to be 2 pi times 1.5. So what's that going to give me? 3 pi feet. That is how many feet in one circumference. which is also a revolution. So now we know the conversion between feet and revolutions. So this is always the formula you use to kind of jump the gap between angular and linear. You have to find the length of the circumference. So 3 pi feet in 1 revolution. Okay, so revolutions cancels. And now we can multiply it out and see what we got. So we've got 1850 times 3 times pi. If I had my graphing calculator, I could type it all in at once, but this one I can't. And then divide by 60. So that's 290.6 feet per second. Right, so if you imagine like on the disk there, something was glued on the edge of that disk and the glue let go, and this object just flew straight off the disk.
That's okay, wow.
That's how fast it would be going. So that's pretty fast. Any question on that? So that's that. So we'll look at a couple things here, but I'm not going to try to finish 6.2 today. Okay, but this is our last section for the week, so we might be able to actually finish it all tomorrow. I don't know. We'll see. All right. So if you've done Socotoa and like opposite, adjacent, hypotenuse, that's called right triangle trig. Right? We are going to do that eventually. But this is what we call unit circle trig. Someone remind me again, what's a unit circle? What's special about it? Chris?
Radius is 1.
Yeah, the radius is 1. So the idea of unit circle trig is that you can give me any angle you want, and I can draw that angle in a circle, just like this. The angle will have an initial side and a terminal side. If I trace this arc, it ends right where it hits the terminal, where the terminal side and the edge of the circle meet. This point has a coordinate. And the whole goal of unit circle trig is to find the coordinate of that point. That's what unit circle trig is. Now, you can't really find the coordinate for just any angle. You can really only do it for nice angles. By nice, I mean multiples of 30 or 45. So that's going to be the goal. You're going to be given an angle. The terminal side is going to hit the edge of the circle somewhere. You put a dot there, and that dot has a coordinate, and you need to find it. That's the idea. Any question on that idea? Okay. So I think this is what I just said. You don't have to write this. So when I say certain angles, I mean multiples of 30 and 45. And the whole goal is to find the coordinate. Once you have the coordinate, that part's kind of important. So I'll just put the coordinate has x and y values, and I think that works now. So the coordinate has x and y values and allows us to find the 6 trig functions of the angle corresponding to the arc we drew. All right. So if you said to me, all right, draw a 90-degree angle. Do something like this. Put my initial side, my terminal side. There's the arc for a 90. There's the terminal point. 90 is straight up. So this is actually one we should be able to find the coordinate for. This is a unit circle. here's the origin, and you went up 1 unit. Because remember, the radius of a unit circle is 1. So what do you think the coordinate would be for 90 degrees? Yep.
0, 1.
Yeah, it's 0, 1. I might say this on the next page. No, I don't. So I'll say it right here. So now, if you wanted me to find a trig function, actually I didn't put in the word function. If you wanted me to find one of the 6 trig functions of 90 degrees, the way I have to do it on a unit circle is I figure out this coordinate first. And I say, okay, you want me to work with a 90, the coordinate is 0, 1. Now I can use the 0 and the 1 to do arithmetic according to the formulas I'm about to show you. What about if you had 180? What would the coordinate be for 180? Wait.
It would be negative 1, 0.
Yep. Negative 1, 0. How about 270? 0, negative 1. And the first one I didn't do, 0. Or 360. It's the same angle. What would be the coordinate for 0 degrees?
0.
Well, 0, 0 would be here.
0.
We are here. 0, 1 is 90. 1, 0. Yep. Those are the 4 coordinates that are the easiest ones to find. Yeah.
Can I know that one?
Yep, just so I know. Any other coordinate, you're not going to have a 0 in, right? These are the only 4 that have zeros. Okay, so any question on that? Did you scan yours?
I scanned bathroom.
Oh. So that's it. Those are the basic coordinates. So once you know the x and the y, these are the formulas that you can plug into. So there's 6 basic trig functions that we use. And the first 3 are sine, cosine, and tangent. Sine is abbreviated SIN, cosine is COS, and tangent is TAN. Now, the formulas for sine, cosine, and tangent are all based off 2 letters, an x value and a y value. If you want to find the sine, you actually don't need the x value. You need the y value, and that's it. The cosine is the x value, and the tangent is y over x. You need both. So if you said, I would like to know what the sine of 90 is, first thing in my head is I think, okay, sine of 90, the coordinate is 0, 1. 0, 1. Okay, they asked me for the sine value. Sine is always the y, so the sine of 90 degrees, the answer would be 1. If you asked me for the cosine of 90, I'd say, okay, coordinate 0, 1. Cosine is the x value. What's the x value in that coordinate? 0. So the cosine of 90 degrees would be 0. And then tangent, I would divide them. Y divided by x. But when I do that, 1 divided by 0, can you divide by 0? No. So anytime you divide by 0, we write undefined. Now, there's 3 other trig functions that some people aren't as familiar with. And that's the cosecant, the secant, and the cotangent. Usually when you abbreviate a trig function, you just use the first 3 letters, but you can't on cosecant, COS, because you already use COS. So they just abbreviate it with syllables, cosecant. And the reason I set them up in a chart like this is because if you know the 3 on the left, 3 on the right are exactly the same, except flipped. So if you think of sine, think of having an invisible divided by 1. The cosecant is the reciprocal. These are what we call reciprocal functions. You flip one to get the other. So if secant is the reciprocal of cosine, what would the formula for secant be? Yep. It's 1 over x. And if cotangent is the reciprocal of tangent, what would be the formula for cotangent? X over y. And again, if you learned it as like opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, that's exactly the same. There's no difference between this and Sakatoa. And I'll show you that when we get to that in a week or two. So any questions on those definitions? All right, so I'll show you this. We'll do an example and then we'll stop, even though we're basically done. I just have a lot of examples of the same thing. Well, we'll do one example and then we'll finish up. It'll probably take 5 minutes to do an extra review example tomorrow. So I think we'll get all of this done tomorrow still. All right, so the quadrantal angles, those are the 0, 90, 180, 270. Those are your 4 special angles. They're special because all the coordinates have either a 0, a 1, or a negative 1. All right, so how do you actually do unit circle trig? Well, I already kind of went through an example with you when I did the sine of 90 and the cosine of 90. But if you want me to write it out, the first step to doing anything with unit circle trig is you have to find the coordinate that corresponds to your angle. Right now, you only know how to find 4 coordinates by hand. 0, 90, 180, 270. There are others that you'll learn how to do. But for now, if it's not one of those, they're going to give you the coordinate. So if they don't give you the coordinate, you need to find it. But if they do, then step 1's already done. So in the first example we're going to do, they've already given me a coordinate. So you don't even have to do step 1 on our first problem. Okay, next, once you have the coordinate, you plug in the coordinate, the x and the y value, into the appropriate formula. How do you know what formula? Well, they'll tell you. Find the sine, find the cosine, find the cotangent. Okay. They'll tell you which one to find. Okay. What we'll do is we'll practice doing all 6, but on a test, you would only have to do 1 trig function per problem. So it might say like find the sine of 180. And that's it. That'd be the whole problem. But we'll practice all 6. Okay, and that's the last notes for this part of the section. The rest is just examples. So we'll try an example or 2 today, and then we'll finish up the rest of the examples tomorrow. Okay. So the directions say the point corresponding to an angle is given. Find the 6 trig functions. So this point represents an angle. What angle does it represent? We could figure it out because we know the 0 and 1s, but it doesn't matter. All I care about is I've got a coordinate. That's the important thing. X, Y. So let's find the sine of the angle. which again, I know I could figure out the angle, but that's not the point. Let's find the sine of the angle represented by that coordinate. Anyone think they could tell me the sine? Wait. So sine, if we go back, sine is the y value. Go back to my point. What's the y value? 1. So the sine of our mystery angle is 1. Okay. How about the cosine? Yeah. 0. So the cosine of whatever mystery angle that coordinate represents, cosine is 0. And the tangent. Well, tangent, now we're going to divide y by x. So what would that be, Chris?
Undefined.
It's undefined. Make sure you can write 1 divided by 0, but then tell me that it's undefined. Okay. Once we get the 3 on the left, what can we do with each one of those to get the 3 on the right? Yeah. Just take the reciprocal. If you don't have a fraction, you can always pretend like it's over 1, if that helps. So Gabe, what would the cosecant be?
1.
1. You flip 1 over 1, you get 1. Next one is the secant. So we have 0 over 1, we flip it, and we get 1 over 0. So what's the secant?
Undefined.
It's undefined. And the cotangent. Well, we had 1 over 0, flip it. 0 divided by 1. What's 0 divided by 1? 0. 0 divided by 1, that's fine. And that's how you do unit circle trig. So tomorrow we'll do another one where they give you the coordinate, and then we'll do one where they give you an angle, and you have to find the coordinate. It's the only extra step here. You got to find the coordinate for 90 first. Okay, so this is the part we got through first. Okay, that's on page 224, 56 to 61, and 70 to 73. And then on 335, if you can't get through all of 335, that's fine. I'm going to give that to you tomorrow anyway with the last part. But if you get 335 done, then you only have half an assignment left for the week. Okay, but you'll have until Thursday to do this one. Okay, so 335 is due Thursday. So in the book, they give you some directions. So I'd like you to do whatever they're asking for numbers 1, 5, and 8. And then the extra thing that I'd like you to do on 1, 5, and 8 is find the 6 trig functions. That's what we just did in the last problem. Okay. And find the 6 trig functions of 3 pi over 2, 2 pi, and root 2 over 2. Okay. We haven't really done any examples of that yet, so you might want to wait on that part till tomorrow. Any questions on that?